Developers coming to Python from languages like C or Java often maintain their existing habits, relying on explicit loops and manual condition checks to process data. While this approach is functionally correct, it forces the interpreter to evaluate every instruction step by step, creating significant execution overhead and increasing the risk of memory leaks. True computational efficiency in Python depends on using idiomatic patterns that tap into the language's optimized backend. We are going to deconstruct a standard data script and refactor its logic using C-optimized native libraries to see how the architecture changes. Code that merely works is a trap if it inadvertently bottlenecks the hardware it runs on. In Python, the equals operator creates a second pointer to the same memory block. Mutating the second list changes the first, causing shared corruption. The .copy method fixes this by allocating a new memory block to clone data securely, ensuring variables remain independent. We see a similar issue with type checking. A standard equality check using the type function is often too rigid, as it fails to account for inherited subclasses. The isInstance function accounts for class inheritance. It recognizes that a Boolean is a subclass of an integer, allowing for more flexible and accurate type typization. Systems built on explicit typing or shared memory pointers become increasingly fragile as the codebase scales. Tracking loop indices manually, declaring a counter and incrementing it at every step, adds unnecessary logic layers and visual clutter to a script. Python's native enumerate function handles this automatically, yielding both the counter index and the list value in a single optimized pass. Merging dictionaries used to require similar boilerplate, involving manual loops to handle cases where keys overlapped between two datasets. The dictionary merge operator introduced in Python 3.9 handles this in one line. It combines the datasets and natively overlapping keys from left to right. Replacing manual logic with declarative syntax removes the human error associated with managing state across every iteration. There is a common professional misconception that Python is ill-suited for large-scale data processing. The speed issue usually stems from the algorithm chosen. For example, using a standard .sort function just to extract the top 5 values in a massive list forces the CPU to sort thousands of items you don't actually need. This chart compares execution times for extracting max values. While the manual sort time rises sharply with the dataset size, the heap queue module stays relatively flat, maintaining a speed advantage of more than 2 to 1. Custom for loops used to count item frequencies also add significant overhead compared to built-in alternatives. This bar chart shows that using collections.counter is twice as fast as a custom loop. It executes the counting logic through an optimized backend rather than the Python interpreter. You can confirm these performance gains for your own code using the timeit module to establish objective benchmarks. Inefficient execution is rarely a language flaw. It is usually the result of bypassing standard libraries designed to handle these specific big O complexities. Nested for loops are the most frequent cause of performance degradation in data-heavy scripts. In a hyperparameter grid search, a nested loop manually traverses every matrix cell to test parameter combinations. The itertools.product function collapses that matrix into a single pass generator, yielding combinations as needed without building the entire structure in memory. You can then use star map to apply functions with multiple arguments across those combinations without re-entering a loop. For filtering, the compress function allows you to use a list of Booleans as a mask, stripping out unwanted data points in a single operation. These tools transform code from a series of manual instructions into a continuous pipeline, improving both readability and execution speed. Beyond data processing, Python's class architecture allows for a clean separation between an object's state and its executable logic. The static method decorator lets you include utility functions within a class without requiring access to instance-specific data. Conversely, the class method decorator allows you to define alternative ways to instantiate a class, making your objects more adaptable to different data sources. To eliminate the repetitive boilerplate of init methods, the attrs library automatically generates attribute definitions and human-readable object representations. Using these decorators shifts the focus from manual object setup to a more organized architecture, keeping the codebase concise and easier to maintain. We have seen how refactoring can collapse complex nested loops into generators and replace manual logic with native, optimized functions. By utilizing these tools, you are offloading the heavy computational work to Python's C-based architecture. Code clarity and execution speed are often linked. Both improve when you use the idiomatic methods built into the language. Before you build a custom loop or a manual check, assume a high-performance solution already exists in the standard library. Your primary task is to find it.